So I'm very pleased to introduce Alex Psomas. Alex is assistant professor of computer science at Purdue University. Before that, he was a visiting researcher at Google Research, a research fellow at the Simons Institute of Computing, and a postdoc at CMU. He is broadly interested, he got his PhD at Berkeley from Christos Papadimitriou. He's broadly interested in problems at the intersection of computer science and economics. And today he'll tell us about fair food allocation.
Thank you. And thanks again for the invitation. Okay. Thanks again for the invitation. It's great to be here. So as a kind of very quick and abstract introduction, a lot of the problems that I think about are about how to allocate resources. These could be organs, vaccines, ads, data, food. And kind of the questions that I ask have to do with balancing some sort of efficiency, computational efficiency, or economic efficiency with things like fairness and incentives. So in a typical theory talk, I would show you a practical problem and then abstract it away into a theoretical abstraction, and then make lemma 3 in appendix F the protagonist. Today I want to do something a little different. So instead, in this talk, I'll be going a lot of back and forth from theory and practice. I'll still start though with a very concrete specific application, and the application is food waste. Okay. So everyone kind of understands that food waste is a problem. Let's see very quickly how big of a problem it is. So in the United States, 40% of the food is wasted, which is something like 120 billion pounds. And 410-ish billion dollars in food are thrown away, which would correspond to something like 130 billion meals. At the same time, food insecurity is a massive problem. So 34 million people in the United States are food insecure. I think these are 2022 numbers from Feeding America, including 9 million children, with a staggering 100% of US counties. So there's no county that has escaped this problem in the United States. Okay. So the problem, how should we allocate food? We're clearly not doing a great job at it. Many nonprofits are trying to help the two problems, right? Like reduce food insecurity and help with food waste. Okay. These nonprofits typically work at very different scales. Okay, so Feeding America works at the national scale. This nonprofit 412 Food Rescue is a map of Pittsburgh, works at the city of Pittsburgh scale. Indie Hunger Network works at the state of Indiana scale. The ACE Food Pantry works at the Purdue campus scale, okay, or the West Lafayette scale. And of course, the scale kind of vastly changes the types of solutions that sound reasonable, or even the way you want to attack the problem. I'm sorry, this slide is very misleading because it makes it feel like I have collaborated with all four, but I have not indeed collaborated with Feeding America. Okay, I have collaborated with the other three. And today I want to talk about the collaboration with the Indie Hunger Network. So the problem we'll see is at the scale of the state of Indiana, which has like 6 million people. And I guess here is Chicago. Indy would be somewhere here. That's a 3-hour drive. So I guess end to end would be something like a 4-hour drive. Okay? I'm not sure how big it is on this side. Probably a couple of hours. Good. So how one of the many things the Indie Hunger Network runs is this program called Food Drop. So here how Food Drop works. You have these truck drivers. So a scenario to think in mind is you're a truck driver. You were supposed to go to Walmart to deliver 300 pounds of avocados, and you show up, and for some reason they don't take them. This could be a logistical problem, like you came too early or you came too late. Or it could be, oh, this top pallet is not good. Now the top pallet could be, 10% of the avocados you're carrying, they still won't accept any of them. Okay, so you find yourself with 200 pounds of perfectly fine avocados. What do you do with them? The outside option is the landfill. You would go and just drop it out of the landfill, then call it a day, and then move on to the next thing you want to do. IHN tries to stop you from doing that. So the way Food Drop works is that you contact IHN and you tell them all your details, where you are, where you're going, how much food you're carrying, why it was rejected, blah, blah, blah. IHN identifies a recipient, and then the facilitate the exchange of information, and then the driver goes and delivers the food. Okay, that's how this works. In numbers, they allocate something like 150,000 pounds of food a year. Okay, so that's the scale of this problem. And who does the matching? A person. Her name is Alex. Okay, Alex Sindorf picks up the phone, from her car sometimes, doing these matching decisions. Okay, like in the weekend from her car, whatever. Okay, she'll do it. So the goal in this collaboration was very, very concrete. Automate this. No human in the loop. Okay, that's what we want to do. And in doing so, because I don't have any humans, I need algorithms. And well, I need to understand how these algorithms work, right? Ideally, I want these algorithms to come with formal guarantees about how efficient they are and how fair they are. Okay, good. So this is a slide I'll be coming back again. So Alex Sindorf is the person who's running the food drop within IHN. Kate, our other point of contact, is the CEO. And this is work with my PhD student, Marios and Partosh. So let's see. Okay, so Alex and Kate described to us some problem. Okay, it's a little fuzzy version of something. And from our TCS background, like, oh yeah, this is a nail. Yes, for sure. Hammers. Okay, I'll show you a hammer. So let me show you what the nail is from the place of academia I'm standing from. It's a fair division problem. It's fair division of indivisible goods. Okay, so I have n agents, the food banks. There's t indivisible items. These are the truck drivers, and every agent I has a value VIT for item t. Okay, and I'll think of agents as having additive preference. So if I give you a subset of goods, then your value is the sum of values. Great. So let's see. This is an example of a problem. A red agent, blue agent. There's 3 items, and these are the values. So what do you do? Okay, you need to find an allocation. These items are indivisible. Here's my strawman proposal. Whoever wants it the most, okay, should get it. So this. Any problems? That's a leading question.
Fairness.
Fairness. Yeah. That's under no definition of fairness would this be considered fair. Okay. Okay, great. So now let's define fairness. The definition of fairness is NV fairness. What's the NV of agent I for agent J? VI of AJ, I's value for J stuff minus I's value for I stuff. Okay. My value for your stuff minus my value for my stuff. That's my NV. Okay, so let's look at this allocation. The thought experiment is that the red agent thinks my value for my stuff is 1.5. I value your stuff at 1. So I don't envy you. Simultaneously, I didn't change the allocation. The blue agent thinks they value their stuff at 0.9. The other person's value, the other person's stuff is valued at half, according to their blue valuation. So I would call this allocation NV3. Fantastic. So maybe I should try to allocate this food in an NV-free manner. Unfortunately, NV-free allocations do not exist. Okay, the easiest way to see this is one item. One item, 2 agents. Who gets it? The other person's envies. Nothing you can do. But that's not a problem. We have approximation algorithms. We can approximate envy. So we can relax it. This is the most popular relaxation of envy freeness. Envy freeness up to 1 good. This was defined in 2004. That roughly says, well, I might envy your bundle, but if I could go and break one of your items, I would be happy. Okay, it's a theoretical experiment. Okay, and the good thing about EF1 is that very simple algorithms guarantee it. For example, the round robin process. If you put all the items in the middle, and agents take turns picking their favorite of the remaining ones again and again and again, the final allocation would be EF1. Great. So I can get fairness, yes, in my abstraction. If defining fairness this way, I can get it. Okay, can I get even more? Okay, now ideally I don't want to only satisfy fairness. Again, perhaps a silly way to satisfy fairness is throw everything in the trash, right? That's also fair. efficiency. So what will I mean by efficiency? I mean Pareto efficiency or economic efficiency. And allocation is efficient if you can make everyone happier without making anyone less happy. Okay? Yes. Fairly standard notion of efficiency. And the big result here is a theorem by Karagiannis et al. That won the Kalai Prize a few months ago. Kalai Prize is a fancy prize in my area that says that finding the integral solution that maximizes the product of agents' utilities is efficient and the F1. Okay. How are we doing? Any questions? It's not competition, it's economic efficiency. I'm saying in terms of the utilities, right? So like, say my utility is 2 and your utility is 5. Pareto efficient would say if for every allocation where I make strictly more than 2, you make less than or equal to 5. So there's no way that I can become happier while you become just as happy or more happy. So for example, any rule that's like a monotone function of the utilities will by default satisfy this. Okay, so product is obviously a monotone function of the utilities, by default satisfy this. A dictatorship would also be efficient. I get everything. Any other allocation makes me less happy. So yes.
I think I'm just having trouble parsing the theorem. Like if you have like a dictatorship where you get everything and all of your utilities are higher than the other person.
That's efficient. That's not an EF1. I'm saying this is both at the same time. Oh no, the product is 0. Yeah, no, it's the product. Yeah. Good. So now this is a big industry actually. Okay, so okay, maximizing the product of utilities integral allocation is NP hard. You know, we have suitable nominal time algorithms for finding EF1 and PO allocations. We know how to approximate M and W, so we know how to approximate the finding an algorithm that finds an integral solution that is approximately optimal with respect to the product objective for additive agents. And you know, this is a very active field. So for example, in stock last year, there was a constant for sub-additive agents. Okay, so this is an area people are working on. You know, change the definition of fairness to something stronger. Some called EFX, that's stronger than EF1, or MMS, or general valuation. This is a very active, rich field. Okay.
So MNW stands for
maximizing Nash welfare. Yeah. Sorry, the product is called the Nash welfare, from John Nash, the John Nash. Good. Yeah. So we have hammers. Okay. We're the hammer factory over here. Okay. Fantastic. So let's try to apply our hammers for food drop. There's a little problem, okay? All of these things require that you know everything up front. Yeah, I can't tell the truck driver, wait for next week to tell you where you're, you know?
Round robin.
What?
Round robin.
Round robin doesn't work because you have to pick your favorite item, right?
Oh, okay, got it.
Greedy would work. Give it to the unhappiest agent or something, yeah? Yes, so the lack of the dynamic nature of the problem is a real issue into bringing these hammers to practice, okay? So in food drop, items arrive sequentially and need to be allocated immediately. Okay, so the hammer didn't work. This was probably not a nail. Okay, so what do? You talk to the people again, okay? And get a little more clarity on the problem. I don't know how well you can see this, but can you see the threads? Yes? Okay. Nails don't have threads. A screw. Yes? Must be a screw. Screwdrivers. I know how to do this. So what's a screw? Dynamic fair division. Okay. So it's the same problem. N agents, T items. Agent I has VIT. Add the preferences. The only new thing is that items will arrive over time. So I'll have an item arriving in each stage for T consecutive stages, and I'll learn the value when the item arrives. Okay. So here's my problem. Burrito comes. I learn the values. Have to make a decision. Say it goes to the red agent. And, you know, they have some value for their stuff. They have some value for the other person's stuff. Burger comes, learn its values. Have to make a decision. Say I give it to the unhappiest person. Pizza comes, learn its values. Have to make a decision. Say I decide to the blue agent the happiest person or something. Go. So value generation is my next slide. Okay, but at some point this game will end, or this process will end, and I'll evaluate the envy. So the envy for the red agent has for the blue agent is half, right? They got a bundle that they value at 1, and they think the other person got a bundle that's valued at 1.5. Okay, and at the same time, the envy of the blue for the red is also half. Okay, so the thing that I'll be interested in measuring is the maximum envy across all pairs of agents. Good. And our question was, how is BIT generated? Okay, and I'll think of this under different kind of standard models in online algorithms. Worst case adversaries, adaptive or oblivious or non-adaptive adversaries, or Bayesian. Another way I think is just the values are Bayesian from a distribution that I know. Okay, so I like to think of this in this kind of line, where the adversaries are stronger on the right. Okay, so the strongest possible adversary works as follows. I write down my algorithm. The adversary looks at the code, gives me item 1. I flip some coins, allocate item 1. They see the coins, they see the allocation, they give me item 2. Okay, and so on. The next adversary, non-adaptive, is the same, but they have to give me the thing at the beginning. Okay, so I write down the code flips coins. They see the code, they give me the whole instance. Okay, of course, I learn the instance as I go, but they have to commit to it. On the other side of the world, the adversary writes down a distribution, and I write an algorithm, and the items are drawn from this distribution. Now, this is IID from the same distribution. The next stronger, every agent has their own distribution. So, agent I has a specific distribution they draw from, and the stronger in this line, in this stochastic line, I guess, is I draw a vector every day. Okay, so you can think of there's a watermelon, and I know how much everyone values a watermelon in this room. There's a banana, I know how much a banana values a banana in this room. And the distribution is, with probability 80%, there's going to be a watermelon tomorrow. With probability 20%, there's going to be a banana tomorrow. Okay, that's this model.
So Anna was asking about just additivity.
Yeah, I think the question was additivity, but if I could be additive but adjust the values, that would also, I guess, an adaptive adversary can do this, right? Where they can give me the next item. It's not exactly what you want. I understand that.
Concavity, for example. You can assume utilities are concave.
I actually can't. That's one of my big open problems. But in a sense, we'll see. Please remind me. Please remind me. But there's a big problem with having stochastic fair division and beyond additive models. There's not many good ideas in the area. I don't know if it's because there's nothing to do or because people haven't thought of it, but it's a thing I care about. Okay, any questions about this line?
I guess the distribution is doing double duty. It's doing it's modeling which items arise in some sense and what the preferences
Yes.
utilities are.
Yeah.
You could imagine some factored representation. I don't know if it does any good.
Yes. You could do. Yeah. Let me. There's a. Yeah. Fair enough. Okay. So let's talk about results. Okay. So let me start with the strongest possible adversary. So, an algorithm that sounds like a good benchmark, at least. You wouldn't, reasonably suggest this to anyone, perhaps, but it sounds like something to compare yourself against is random allocation. Adam, come give it at random. Okay. And now for this algorithm, the fairness guarantee would be that the expected max envy is hiding log factors root t by n. T is the number of items, n is the number of agents. Think of it as this comes from random walks, okay? Like the precise thing is multicolor discrepancy is what causes this. Unfortunately, this is not very efficient, okay? Because you're giving the items at random. There could be some way to improve someone by a whole factor band, right? Like think of a diagonal instance, right? Or like item 1 is only valued by agent 1, item 2 is only valued by agent 2, and so on. This random would be something terrible there. Good, but this is.
I guess that's a really interesting thing because I think for the specific application, and I know you're going to go back and forth between the theory and the applications, but for the specific application, you could imagine there's some bounded variation.
Yes.
That values for the same item are within a factor of 2, to be even generous.
Yes, and this is what will make this tight, right? Like the all ones is what makes this exactly tight.
Yeah.
Yes. But I could still hope to beat. So a good thing about this fairness guarantees is that it's sublinear, right? In the number of items. Like your average NV is root t by t, right, per item. So in no regret learning, they like this sort of thing, right? This is success. Still, like you could hope to either, maintain this sort of fairness guarantee and maybe improve on the efficiency. Or even for now, like improve the fairness guarantee. Unfortunately, the fairness guarantee cannot be improved. So root t by n is tight against the adaptive adversary. So if the only thing you cared about in the world is minimizing the maximum NV, you wouldn't be able to beat root t by n. Okay. So random allocation is asymptotically optimal in terms of its NV guarantees. So, okay, my other question was, let's keep it then, and then improve the efficiency to better than 1 over n. Okay, I want to do something that's not silly in terms of efficiency and still have this like sublinear NV kind of guarantee. Oh, sorry, I had a lot of names. I showed my students, I should show everyone. So this is 2 papers that were combined to one journal paper with Herdis Benade, Alex Hazarskov, Ariel Prokacha, and David Zink. I don't know how to cite these sort of things where it's 2 papers merged into one later. But the next result in this thread is that you actually cannot. So even against a non-adaptive adversary, if you want to do sublinear NV, so your NV being t to the 1 minus epsilon, you cannot be 1 over n plus epsilon Pareto efficient. Okay? So basically, you should either be a dictator, in which will be efficient. So either give everything to the same food bank, that would achieve perfect efficiency and horrendous linear NV, or randomly allocate, which would be square root t here and 1 over n here, and nothing else. Like there's nothing that's like stochastically dominating these 2 options. Okay. Yes.
There's no computational efficiency here, right?
No, no computational efficiency. There's economic efficiency, Pareto efficiency. I mean, dictatorship and random happen to be computational efficient. But yeah. Okay. So far, so good. So if you believe the world to be a very, very bad place, there's no interesting design for you. Good. So let's swing far on the other side. Let's see what happens here. So here, the answer actually came from a paper that wasn't studying dynamic fair division, but just stochastic fair division. So if you just give every item to the agent with the highest valuation, this is obviously Pareto efficient. Right? We maximize the sum of values. And it's also NV-free with high probability. Okay, let's see why. Let's yes.
Is it EF1 or is it just
EF with high probability. Okay, this is not a worst case instance. That's how I could even hope to prove something like that. Let's see the proof, and let me show you the proof for a uniform 0, 1. So say VIT is drawn from uniform 0, 1. Your expected value for tomorrow's item is half. Yes. But now your expected value condition on you getting it, so condition on you being the highest is like 1 minus 1 over n. Yes. Now your expected value condition on someone else getting it is less than half. Yes. So there's a constant gap between an item you get and an item you don't get, and everyone roughly gets the same number of items. Okay. But every time you get an item, you increase. Okay, so Chernoff plus unit bounds, and you're done. Okay. And the same proof would go through as long as kind of these conditional expectations had a constant gap. Yeah. That's it, by the way. Good. So here, good news. Give every item to the person that wants it the most, and we prove high probability. What about over here? Every agent draws from their own distribution. The same idea doesn't work, right? Because I might be drawing from uniform 0, half. You might be drawing for uniform half 1. Now you'll get everything. Okay, maybe quantile space would work. Give it to the agent with the highest quantile. That doesn't quite work either. Think of uniform 0, 1 and uniform half plus minus epsilon. Yes, the problem here is that agent 2 only cares about how many items it got. So this would be NV free to high probability, but not efficient. It's very likely that I win some items for which my quantile was low, and you lose some items for which your quantile was high. So there's going to be some trade that we're happy with. I'm always happy with if I'm agent 1, I prefer 1 high value to 2 low values, but you always prefer 2 to 1. So there's going to be, with high probability, some trade that can improve both of us. Yes?
Just to make sure I'm clear, you're saying you give it to the agent such that like the valuation of that item is highest sort of
In quantile space. Yeah. In quantile space, we're both drawing from uniform 0, 1, and we're mapping it using, some different function, right, to go back to value space. I'm saying just look at quantile space only. Whenever your quantile is higher than mine, you get it. I'm just saying, like, in value space, what's happening is that, like, you'll say care only about the number of items you got, and I actually care about the scale. So there's, with high probability, going to be some trade that we're both find beneficial, which breaks Pareto efficiency.
Are you you're assuming that you know the distribution?
Yeah.
Yes. I assume that I know the distributions.
Is it a half efficient in this particular example?
I mean, for 2 agents, everything is half efficient. Everything that's completely, not silly is half efficient. Yeah. But Bain Golds gave a EF with high probability, Pareto efficient, and computational efficient algorithm for this problem. I'm not going to show you the algorithm, so I'm going to show you my own result, which is for the stronger setting. In fact, even in the stronger set, this is a funny thing because this came before this, but this is not computationally efficient for this because of the representation, but whatever. So the result for correlated items is that you can be Pareto efficient exposed and have this kind of bizarre fairness guarantee. So between I and J, you're either going to be NV free to high probability or EF1, one of the two, with probability 1. So that's the kind of personal guarantee you can say. You say, hey, you, like, either I will not envy you with high probability, or if I do envy you, at most 1. Okay. Good. Now, what is with high probability this? Yeah. No. The failure mode of this bullet is envy. By more than 1. But if the probability that you envy is more than, say, like 1 minus 1 over t, then your envy is at most 1 with probability 1. It's a strange type of guarantee. Agents basically fall into 2 groups. Okay, you can think of like you either fall into group 1 or group 2. Group 1 within each other will have EF1. Group 2 within each other will have EF1. And across groups will have envy with high probability. That's how the actual algorithm will work. Okay? And you know your group. I can look at the distribution and tell you which group you'll belong to. Okay? So it's not the case that with probability, like, it's not the case that exposed your envy is always small, if that's the question. Okay. Good.
So I guess I'm going back to my other question. If you factored this distribution, right? That is to say, the distribution of items is unknown. So which items you're going to get?
I don't know.
But for each item, there's a much more restrictive model of the utility. Like everybody, I don't know.
I say everyone is, say, submodular within this or something like that.
Yeah, or
concave
or even nearly the same.
I say the other way. You could do this, but again, I can get positive results without doing this.
Yeah.
So the question is, can these help me get away from those, right? Like, if I can get positive results here, I'm only interested in getting positive results to the right.
I see it.
Yes, in some sense. Or unless I'm unhappy with this algorithm for some other reason, like complexity. Exactly. And let's see. So let me give you some intuition about this algorithm. One of the kind of initial problems with thinking about this, how could you ever hope to be Pareto efficient exposed? That seems like a too strong of a guarantee, right? You're saying, like, no matter what happens, there's no way there's any trade that improves to people. Like, how are you doing such a good job without, like, greedily maximizing some, like, function like sum, right? Like, that seems like the only way you could do this. So let's see, let's take this instance, for example. So I have two agents, and I know burgers come with probability 0.1, and pizzas come with probability 0.9, and these are the values. Now, obviously, this is efficient. Yes, there's no way, no matter how the pizzas and the burgers come, that I'm going to find a trend. No one wants to trade, no matter how many pizza burgers come. However, this is not fair, right? Because 90% of the time, you're going to allocate to the blue agent. So the first kind of insight here was that you can be Pareto efficient here in this instance. This instance will be key for the way the algorithm works. So I just multiplied, right, the probabilities into the instance. So the blueprint for my algorithm is construct this instance, I, and I'll find a fractional solution, x star, for I. And then online, every time item k comes, every time the pizza comes, I'll give it to agent I with probability x star ik. And kind of the first lemma is that if x star was Pareto efficient for instance I, then online this will be exposed Pareto efficient. Okay. Now the second lemma is that if x star is fair, we can give fairness guarantees. However, if you want to get NV freeness with high probability and avoid the square root t's, NV freeness for x star is not good enough, right? If the expected NV is 0, the random walk will lead to roots. You need the expected NV to be negative to get NV freeness with high probability. And before this, it was not known if I give you an offline instance whether you can find a strongly NV-free Pareto efficient allocation. And in fact, you can't. You need conditions. And that's where the bizarre guarantee comes. Okay. So the structural result here, which is the driver of everything, is that for an offline problem, if I have n agents and m items, there exists a Pareto efficient fractional allocation x star with this fairness guarantee, either strict NV or identical allocations. The strict NV with Chernoff will give me NV free with high probability. The identical will give me EF1. Okay.
You're saying the rounding algorithm intrinsically turns identical allocations into EF1.
I lied. Sorry, you got it. I don't quite do this. So if you're in this bucket, I do something slightly different. I slightly lied. Sorry. I thought it's not the level of detail that is good for a talk. Sorry, but you got it. Okay. Okay. Good. So the takeaway is in the stochastic world, as long as kind of there's independence across time, I can do good things. In the non-stochastic world, I cannot do good things. So what are the natural kind of future directions? Oh, sorry, I have my screwdriver. Okay. What are the natural things? Can we escape? And we have some results on this form. So for example, if you force your adversary to write down an instance that adds up for the same number across agents. So this is the predictions model, if you've heard of it. Like I ask you, it's very popular in algorithms these days, like pure algorithms. Like I promise you that the total sum of values across all t items is going to be 1. If you have such a sort of constraint on the adversary, you can do something not devastatingly bad. Okay. The other one is, can we get even more? Can I ask for more? And let me show you one result that I really enjoy in this. Can we get more? Let's say the items have values, but I don't know them. Okay? People, as it turns out, are terrible at telling me, like, what's my value for this? What's my value for this? I know I prefer the phone to the water bottle, but if you ask me for numerical values, I'll probably do a horrendous job at it. Okay? So the items have values, but I just never learned them. I learned the rank. So here's my, this is joint work with Herdis and Daniel. Here's my model. Burrito comes, there is value, but I know nothing. The algorithm knows absolutely nothing about these items, has to make a decision. Now the burger comes, the burger has values. The algorithm knows nothing for the blue agent, and it knows that the burrito is better than the burger. Now it has to make a decision. Pizza comes, the algorithm, the pizza has values, just don't know them. The algorithm knows that the burrito is better than the pizza, and the burger is better than the pizza. So what now? shockingly, at least for me, in the IID model, you can get a 1 minus 1 over a squared approximation to welfare, so therefore correct efficiency, and NV freeness with high probability. And you can get a slightly lesser constant, but still a constant for the non-IID model. Okay? So you can get like a really fancy screwdriver, okay? But it was very hard. This is a note. It's very hard to online find fancy screwdrivers. So this is actually AI generated. So Gemini, the Google machine, told me, here's a go at the fanciest, most impressive screwdriver you've ever seen, designed to be impossibly cool. Okay. So so this is kind of my understanding of this problem. Demand for more, escape by weakening. Let me mention a few things as a final note for this guy. I cheated big time. The way I cheated is for these results, I took t to infinity. Yes, I double dipped. Right here, it was known stochasticity, and t was picked by the adversary. Here, the adversary wrote the distribution, and I took t as large as I wanted. Yeah. So this problem is significantly harder. So for two agents, the interest of these papers was discrepancy, online discrepancy, not fairness, but you get results as a corollary. There was a polylog bound in this adversary by Bansal et al., which was improved to n agents, multicolor discrepancy, by the same authors in SOTA 21, which was improved to log nt, stock 21, against even the oblivious adversary. Again, multicolor discrepancy. Which was improved to square root log nt by Kulkarni et al. I'm not sure if this is published or not. I have an asterisk because I found out about this last week, about this result, and they prove this for two agents, they prove this for discrepancy, which implies NV guarantees for two agents. I'm almost sure, but not 100% sure. These people give a reduction from discrepancy or extension from discrepancy to multicolor. I think they go through, which I would get my result, but I don't know for sure. Okay, if it's not true, don't kill me. Okay. Yes. Okay. So and this is for discrepancy. This is tight. Like for discrepancy, there's a match in omega log square root log n or square log t by like log t, something lower bound here. So this is for this, they cannot help us anymore. Okay, we need to look at NV if we want to beat this square root log nt. Okay, but these, if you don't want to cheat, in a sense, these problems are harder. Beyond additive, these are the questions. Of course, for the hard problems, they're still hard. What does it mean to draw a beyond additive evaluation? What does it mean to draw a submodular evaluation? I can always pick it. No matter what family you give me, if the family includes the some modular valuation that you only value one item, there's nothing you can do. Yes. So there's no good stochastic models about beyond additive. We have models for these sort of things for auctions, but they're kind of useless for fair division. If you care about this, please talk to me.
Can you say that again?
There's no one in stochastic fair division. So this is just an area, right? Stochastic fair division. Like under what conditions do NV-free allocations exist with high probability? There's nothing you can do. Like so people draw beyond additive in two ways. One is I have a family of some modular say valuations and I draw from it. Okay, I can create trivial instances where there's no NV-free allocation, but just like having some modular functions where you only like one item, or everyone likes one item. Nothing you can do. The other model we use in auctions is this independent over subadditive model by Weinberg and Rubinstein. And that also has the same problem. You pick a worst case submodular function, and there's randomness in the types. Useless for NV-freeness. Because again, you can hard code functions that have no NV-free solutions. So it's not even clear how to ask the question. Yeah. Good. Okay. But let's go back to practice. Okay. Fantastic. So I have fancy screwdrivers. I can do this. Okay. So here's a truck driver. They're at Gary, Indiana. They just had a food load rejected. They want to go to Kokomo, Indiana. Okay. And here's a subset of my Or say, here's the food banks that are open, okay, these 4. Okay, now I can use my various screwdrivers to allocate this good, right? Like whatever algorithm you like the most. Anyone sees a problem though? Driving distance, yeah? We know that food doesn't have preferences of who eats it, but the drivers who deliver the food definitely have preferences. Yes? Yes?
I guess before we move on to that, the furthest right possibility result you gave required explicit information about distribution, right?
The furthest green?
Yeah.
This? Yeah.
Yeah. So in practice, when you're deploying this, like where is this information coming from?
As data, you could say. You could say I'm running something, like I'm looking at what the human did. I mean, I can't because their data is not good. But I could, do something. I can run one of these and pretend, and then look at what happened. And again, like once we're closer and closer to the practical problem, I'm allowing myself to be a little arbitrary for the sake of progress. Okay. But as Peihan said correctly, some reciprocation required too much additional driving. Okay, that my model didn't capture. Yes, because my model didn't have 2 side preferences; it only had 1 side preferences. Right. So in my model, food didn't have preference. Of course, food doesn't have preference. Drivers have the preference. Okay. So back to this. Right. So I thought it was a screw, but it's actually it's an Allen screw. Okay. Like the IKEA kind. Okay. So I need an Allen wrench. Okay. But still, I have a reasonable set of theoretical results here that I could hope that I could still help. Okay. So I'm at the crossroads somehow. So I can use the existing theory, which is rich, to have some heuristics that work well. Okay. I can really try to jam that screwdriver in the Allen wrench and make it work. Okay. Or I can do some new theory. Okay. So for the last 10 minutes, let me show you some new theory that's under submission right now. It's very fresh, and there's an in. Okay. Like I'm similar to the connection to discrepancy. I'm going to show you a connection that I find very interesting with a completely kind of different part of theoretical computer science. So my new model is graph-based. Okay. So I'll think of having a graph, and I'll have edges with weights corresponding to the distances. And each node will have also weight corresponding to the food insecure population. Okay, and some of the nodes will also have food banks. So I have a graph. Some nodes have food banks. Every node has some population. The nodes you can think of as counties. And I'll assume that every individual is served by the food bank closest to them. Okay, under my metric. So now in my problem, drivers will come one at a time. A driver around T will sample a node to be its origin, will sample a node to be its destination, and will sample a value. That's how valuable the food they have is. Okay.
Sorry, why is the destination drawn?
Oh, they're going somewhere. No, these are people, right? Like they're like, I was gonna I'm at Chicago. I have 200 pounds of avocado. My next kind of destination, either because they live there and their shift is ending, or just because they're delivering something else there or picking up, they have a destination.
So they're gonna drive from X to the food bank.
That's their goal, right? Like, yeah.
Then drive to
Yeah, in a sense, if things have gone well, they would have gone to Y, but things didn't go well, and now they have all this extra food. What do you do, right? Okay. Good. So now, drivers arrive over time and must be matched. Yes.
Arrival at Y?
Huh?
Upon arrival, meaning arrival at Y?
Arrival at X. They're at X, and they want to go to Y, and I want to match them to a food bank without, X to food bank to Y being small.
X to food bank.
Food bank to Y.
Y is like the next.
Y is the next place. Yeah. Like it's your house. Okay. This is like 5 p.m.
It seems odd that X and Y would be drawn independently, it seems like.
It's independently.
Yeah. It's a little bit, maybe all the time Y is X. They just want to go home.
Yeah, but for someone who calls you at 9 a.m., it's unlikely that they're still working, right? Like the truck driver. Yeah.
There are situations where.
Indeed. This is not a perfect model for sure. The W is the weight of the food you're carrying. Not every truck driver has the same amount of food, right? Yeah. And that I still assume that's stochastic. Okay. So regarding D, the assumption here is that in reality, in a sense, you would expect drivers to show up in a county proportional to its population, right? That's how commerce works, right? There's more commerce in places with more people. But the guarantees that I'd like to give, with fairness, of course, will have to do with the total insecure population. And as it turns out, these two are related, but we'll see. So I'll call a distribution alpha beta biased if basically it's within a 1 over alpha or beta of the of the true kind of proportional, right? So the probability that the distribution samples a node V, this is the true kind of proportional probability. Food insecure population, total food insecure population, 1 over alpha beta. Okay, so I'll call this distribution alpha beta biased. Okay. So what's fairness and efficiency here? For individuals, kind of this is matching the previous fairness guarantees. Something is multiplicatively envy-free, say 1 plus epsilon, if the gap between the happiest and unhappiest person is 1 plus epsilon. And I also want, at the same time, driver efficiency. Right? So the previous question, so if you're a driver X, Y, W, X is your origin, Y is your destination, I want the amount of distance I tell you to travel, X to F, F to Y, F is a food bank, to be a delta fraction of the optimal. I cheated a little bit in that this optimal includes a food bank. Ha. Yes? Okay. So very, very quickly, what are the results here? You cannot be 3 minus delta and anything envy-free. So if you want to be better than 3 minus delta driver efficiency, your envy guarantee is as bad as the number of nodes. Okay, so very, very bad, super constant. What's happening?
It's just the projector.
Just a projector, right? Because everything else works. Okay. I'll try and not touch it. And at the same time, we give a tight matching algorithm. So we have a 3 driver efficient and 1 plus epsilon envy-free algorithm where epsilon is something. But let me tell you the algorithm, and hopefully now you'll see why I decided to present this last part. For every round, I'll find the food banks, FO and FD, that are closest to the origin and destination, respectively. And then I'll match to the food bank that's the unhappiest of the two. Okay? That's my algorithm. What is this? Any takers? Does this ring a bell? Let me give you one more. Sorry, this is asterisk about constants and whatnot. But let me give you. Does this now ring a bell? Yeah. So balls and bins. Okay. Let me. I mean, for this audience, I don't really need to. Say I have n balls thrown into n bins. I pick a bin, a ball uniform. I pick a ball, and I pick a bin uniformly at random. Bang, bang, bang. The expected max is m over n plus O roots, right? Power of 2. I pick a ball, pick 2 bins at random, put it the lightest.
Shouldn't need it for this audience either.
Yeah.
Ellie's not here, I guess.
M over n log n. Yes? This is, sorry, I cited the m equals to n work here by Azar et al. The heavy loaded case where m is bigger than n is by this paper. But this, if this is the first time you see this, you should be absolutely shocked and thrilled that this additive error does depend on the number of balls. Okay, like that you shouldn't believe, and you should be Googling, Alex Psomas liar question mark. Okay, but it is indeed the case. Okay, so there you go.
You've never seen Power of Two Choices. So. I guess Ellie and others won the some prize for it. Which prize or
I mean,
Kyle X prize, I think.
not only one prize, I would assume. Yeah, this is yeah, this is yeah, this is yeah, amazing. Okay. So our contribution is a little different. Okay, so this are my children. So if you see the bins are not all equal size, yes, because the food banks don't have equal size. They're also not uniformly selected. This thing doesn't actually shoot them all, uniformly at random. And also, you can see, but these are cars, and the thing that's about to go is indeed a choo-choo train. Okay, so the balls are not equal either. Okay. So our contribution is somehow balls and bins power of two choices guarantee for non-uniformly weighted bins, non-uniformly selected probabilities. I don't pick exactly two uniformly at random, and randomly weighted balls. Okay, so I need all the elements. And I'm not going to talk anything more technical, but there's a lot of, this is a big industry, okay, it's a very rich industry, and many people had studied like one or maybe two of these at the same time, but doing all three was a non-trivial endeavor. Okay, that's all I'm going to say.
Can I ask about the theory? I have a
Yes.
question about the lower bound. I have no intuition at all. Does it depend on the metric?
The metric?
The lower bound.
The lower bound on power of two?
No, the lower bound for your result.
Yes.
Going way back.
Okay.
We don't have to go back, but
Okay,
you
sorry.
had
3 minus delta. Yeah.
Does that depend on the metric?
On the metric.
If you had special metrics, is you go weaker lower bound?
Oh. I mean, sorry, I didn't say this, but my graph obviously satisfies triangle inequality, but nothing else. So I don't actually know. I don't know the answer to the question. Yeah.
Like if you had, like if everything was on one line, for example, can you still get the same lower bound?
I don't know that. I don't know that. My graph is a star with like almost a lasso thing, but for a line, I don't think you can do this for a line. But the interesting thing is that in experiments, we run this with synthetic data, okay, from Feeding America. In Indiana, okay, there's the driver optimal algorithm. There's a driver optimal algorithm, so always match the closest. There's greedy, which says like give it to the unhappiest person. And greedy with cutoff is, in a sense, if you only knew the second part of the talk, the screwdrivers, you would come up with greedy with cutoff. It's some like kind of do round robin within like a certain kind of radius. Algorithm 1 is algorithm 1. So greedy with cutoff does great in Indiana. It's actually kind of better than algorithm 1. But for California, thanks to Santa Cruz, as it turns out, there's no cutoff that greedy with cutoff works. There's something about being isolated and having a food bank that like is very bad for you.
So this is synthetic data, but based on real location.
Real food insecure and real population. So we sample from the real population. And the weights are completely synthetic, okay, of the food donations, but everything else, the distances are real. The locations of the food banks are real. Everything is real. And I am proud to announce that as of April 17th, so last Wednesday, this is actually running. So algorithm 1, if you go to fooddrop.org, power of two choices will match you. Okay, don't do it because you're not drug drivers. But okay, so next time, hopefully, I can do this with the real data. Okay, thank you. Questions? Yeah, I guess there were so many questions already. Yeah. So.
I guess the question during the talk, sorry, it's not recorded.
No, I think it's too much running around.
Yeah.
I had a question.
Yeah.
To show the various algorithms that has different trade-offs.
In the last thing you're saying?
Yeah, I was just wondering how you pick which one. Like, are they happy with the trade-offs that you're making here?
Oh, you mean in the actual application? I mean, they're happy to not have to answer calls from their cars, to be completely honest. with you, but we haven't been running long enough to get this sort of to get pushback of like, oh, this is terrible. Where are all my donations, sort of thing. So fingers crossed. You know. Yeah.
So to run this, does like a driver need an app then?
No, it's all text-based. That's why actually I didn't show you any figures. Like I'm just gonna show you. I guess I should make figures of text, but like, yeah, they go online. What happens is they go online and they have a form that we built. I mean, maybe I can show you, but maybe I can show you after.
Like,
But
what replaces the phone calls?
what replaces the phone? Texts.
Okay, so then
Text.
you're texting to
Yeah. So it used to be the driver talks to Alex, and they tell Alex like, okay, I'm there, I'm going there, probably in like 30 minutes I'm leaving, like I'm carrying this load. Okay, and Alex closes and like. It's like, who is the best texter? It's like, okay, like Alexa, text Matt from Midwest Food Bank of Indiana. Okay, Matt, do you want 100 pounds of avocados in the next hour? And now all is done. So now the driver filled out the form. The backend runs power of 2 and texts the recipient, hey, do you want this? Here's a picture of the load. Here's a bunch of stuff. Yes, no?
Yes, the food banks are not automated.
They're still, yeah, exactly. We didn't do it that much. I think that's a recipe for disaster because, for example, they couldn't even tell us the hours they're opened. Because they would say, okay, like officially we close at 5:30, but happy to accept a large load at 7. So those things are, not codable, right? Like happy to blah. Okay, you get a text, you decide. Okay, so this. Yes, it goes down the list, exactly. Yeah. And how fast, right? Like if they're not responsive, 15-minute cutoff. Like even that, we don't know how it's going to work, right? It's 15 minutes. It was just a domain thing. Like we sat down in a meeting with all the food banks and we're like, how long is good enough? Like, yeah.
Yes. Are there interesting theory questions on the food bank side? I mean, all of the model food bank would just kind of take what's given to them. It sounds like it's not the case in practice.
I would say one interesting problem. It's not quite on the food bank side, but like it is on this thread. Is the latest graph-based model assumed that all kind of food banks are somewhat identical up to the number of people they serve, but that's not the case. So for example, some of them have more fridge space or something, right? So to do something like that, if you want to stick with the algorithm, you will need vector balls to vector bins, which I know nothing about. So if you ever want to work on balls and bins, but vector balls, go for it. Okay, you have my endorsement. But that I think could be interesting. I don't know how theoretically hard it would be, but that's one thing that comes to mind.